and leaving only one in the queue. So that is the only way possible in a queue system setup to draw the distribution of the customers if we are told that there are 4 customers in the system. And if we are told that there are only 2 customers in the system, then it has to be this. Well, there can be more than one. It can be S1, S2, S1, S3, S2, S3. So there can be a few configurations. But if there are 3 customers, it cannot be like this. 2 customers are being served, one server is idle, and 1 customer is in the queue. It cannot be like this. Okay, it is forbidden. Although in real life anything can happen, but for the sake of analysis, we don't allow those configurations to be possible. All right, let's look at how the numbers play out, right? So earlier on, we did say that lambda has to be less than rho for the queue system to k mu, sorry. Lambda has to be less than k mu for the queue system to be stable. Then we come to this diagram and learn a few things here. Let me just repeat out a few of these symbols. All right. So first thing first is let's talk about rho. Rho is the server utilization, if you recall from our previous discussion. And what rho means is how busy a server is. But last week we talked about only one server, so a server is simply refers to that server, right? It's clear. And rho refers to some sort of a percentage, a number between 0 to 1, to reflect how many percent of the time, if you snapshot the server 100 times, how many times would you see that the server is busy? So we notice that the server is busy when it is facing a customer. All right. So when there's a pairing between customer and a server, then that server is busy. So we understand what rho refers to, and we calculated that as lambda over mu. This week, we're going to expand it to k mu, where k is the number of server. And if k is equal to 1, then we fall back on to last week's discussion on single server, lambda over mu. So it is consistent. So with more than 1 servers, then we have lambda over k mu as our percentage. Again, what does this percentage refer to? Does it mean collectively? Does it mean single server? Well, it means both, because every server is identical. And so if one server is 50% busy, all the other servers will be also at 50% busy. It cannot have any way from this formula. There's no way to point at S1 is the one that is 60% busy, S2 50, S3 40, therefore as a whole collectively on average we have 50%. No way. No way to say that, right? So basically that number refers to each and every server having rho percent or rho fraction amount of the time being busy. So that's the server utilization. But we also see this where we momentarily throw away the k. So this is not a typo, this is on purpose. The lambda over mu has got frequent appearance in the mathematical derivation. Let me just fast forward a little bit to show you as an impression, right? Over here, we'll come back to the previous slide again. So there are a lot of lambda over mu's appearing everywhere in our formula sheet. So much so, in fact, this is also lambda, because if you cancel this out, this is lambda over mu too. So lambda over mu is a factor that pops up everywhere. So much so that we have to think that there must be certain significance about it. And it indeed seems to be so, and it sort of earns itself a name called implied utilization. Implied utilization. So what this means is, it is implied means it's not happening. It is not happening in real life, but it has got that implication there. So let's be more concrete about what that means. Here, our k equals to 3. So we have 3 servers, and we have k equals to 3 servers. And what implied means is should any two of them, that is, all the servers go down except one. All right, so should any server, in fact, should all servers go down except one is operating, and the arrival rate continues to be lambda, so you're now not served by k mu capacity, but you are served by just mu capacity. How serious will the situation be? So I think that would be how we can think about implied utilization. So to put that in words, implied utilization, we just put in quotes because it's more like a way of thinking rather than an official definition, right? So how severe the situation would be if all but one server fail to operate. So the higher, the worse the situation. Okay, so if the implied utilization for two queue systems, that they come in handy if you have to compare, right? So two queue systems, both have incoming arrival rates lambda. One has got 3 servers and another has got 5 servers, right? So let's compare these two. Yeah, okay. So in our case, if the k increases, then the implied utilizations for both cases are basically the same, lambda and mu, because we have lambda coming in and mu, and there are k equals to 3. We have lambda coming in and mu, and k equals to 5. So implied utilization refers to lambda over mu. So in these two queue systems, they are basically having the same severity. Now, what does that mean? So how should we react? If they are potentially having the same severity, because should all servers but one, right, fail? That means we are talking about contingency planning. What if all servers but one fail? How serious would it be? So lambda over mu for both cases are the same. So let's not make this a big issue, as if k equals to 3 tends to be more threatening. All right, so that's how implied utilization will be able to inform us about that. But suppose it's not only that, not only k is different, right? Let's say this is well, if the lambda, if the arrival rate towards the k equals to 5 system is, let's just put it as unity lambda, but this is 2 lambda, right? So that means the real lambda is actually 2 times of that goes into the 5 server system. So in that case, we have 2 lambda over mu versus lambda over mu, and that's like twice as much. So we then now say that, well, the implied utilization for the 3 server system is pretty high, much higher than that for the 5 server system. So I think we should have more budget for standby in case something fails. Not that it will happen, not that we plan to happen, but we are just saying should, right? Should it happen, then we should have all these contingency planned out more thoroughly, in more detail, with greater amount of budget to handle situations for the 3 server system than for the 5 server system. Why should we do that? Because upfront we know that the implied utilization is higher. Okay, so that is just one way for us to digest what this number means, and of course, adding to the fact that we see this very often in the formula helps us to appreciate its importance in the overall scheme of works. Yeah. Okay. Now, what are the formulas? We had a peek at this just now, and now let's look at it full front and center. And they are like that. But the point here is not to be too engrossed into the formula calculations. What we should do, however, is to first of all note that there are 2 probability formulas here, right? This is P0 and Pj. All right, Pj when j is more than 0. So P0, as we recall, is the probability of having nobody in the system. Nobody in the system. So nobody here, and if there is no one in the queue, then there cannot be any, well, that's not true. Well, there may be someone still being served, right? So nobody in the queue and no one being served at all the servers. Zero. What's the chance of seeing that when we randomly take a camera and snapshot at the bank? Nobody in the system. But of course, the servers are standing by, but nobody is there. Maybe nowadays it's quite common to find this, right? Because of COVID-19 and all, and we can find many shops. If we randomly pick a shop and at a random time and we take a camera snapshot of the shop, the physical shop itself, we might find that the servers are there, but no one in the system. So what's the chance of seeing that? That's what P naught qualitatively tells us. And because it has this physical effect, if this chance is high, means our shop is not frequented by customers. Not many customers are in there, right? If this chance, this probability P0 is low, that means the chance of having more than zero customers, that means at least one customer, is higher. And that is typically a better thing to retail owners than otherwise. So since it has that implication, we need a way to quantify it. And this uh, humongous looking formula is our savior. All right, so it's a helper. It's not something that is so unpalatable. Of course, if you're running your business. Now, so it helps if we first calculate what is lambda over mu when you're performing your quiz or exam calculations. It helps to calculate this number first because it appears everywhere. Even here, we can divide through by mu to arrive at k over k minus implied utilization. So using our earlier example when we said lambda was 3 and mu was 4, then our implied utilization lambda over mu will be 0.75. Okay. Now, actually, this is not a good example, I would say first, because typically when lambda itself is already less than 1 times mu, it's not a good business reason to deploy more than one server, unless there are other reasons such as um, impression to the customer, quality of service, those other angles of assessing whether the system is good or bad. But strictly from the queuing perspective point of view, when mu is already larger than lambda, there's no reason why we should deploy yet another server, which is going to cost us money. So typically, when we come to multiple server, we would expect mu to be smaller than lambda. So for example, suppose mu is 2. Okay, so that gives us a reason why we might need um, 2 servers instead of 1, right? 2 or more. Yeah. So in this case, now updating our implied utilization, it will now be greater than 1. So don't be surprised if you see this implied utilization being larger than 1. That's okay because it's kind of hypothetical. It's not happening in real life. It's just happening within the theoretical framework. Yeah. So typically, in fact, in multiple servers, we should expect lambda over mu to be greater than 1, or else the system will be kind of wasting money, running more capacities than is needed. So we have this number that is bigger than 1 raised to the power of n divided by n factorial. Okay, and then we sum it up, and so let's just try to see what we do here. Okay, and then we have this again. We have this 1.5 and k over k minus 1.5, and then the whole thing, the whole denominator is summed up, and finally we take a reciprocal. Let's just do this as an example. So we have lambda equals to 3, mu equals to 2, k equals to 2 servers. Check that lambda is less than k times mu, right? So the system is stable, can survive. Calculate lambda over mu, that's 1.5 because 3 divided by 2. And we'll focus on the denominator first. Okay, so the denominator d will be summation of 1.5 to the power of 0, right, times or divided by n factorial, 0 factorial. So first set n equals to 0,